Okay, so we had just talked about the idea that whatever column these elements fall into, that gives you its valence electron, and those valence electrons determine that element's reactivity. All right. So here's your definition of that valence electron. Okay? And this, well, we could say it's always important, yes. At this level we talk about it, but for those of you who go on to take general chemistry, these are really important, okay? Because you go on to talk about what we'll call quantum numbers. And you have to be able to classify these in order to do that. So we verbally talked about this, okay? So can anyone give me an example of a transition metal? And what element is it? When we say what element is it, we say we want the atomic number for that. 21, okay? So what block is that in? It's in the D block, okay? How many columns are in the D block? There are 10 of them. Now, I can't stress this enough. This number 8 that we talk about is the S block that holds 2, the P block that holds 6. That's where this number 8 comes from. Your S block, column 1, column 2, and here's your P block that has 6. It's those two numbers added together that gives you an outer valence of 8. And we can illustrate that, okay? So what we mean by that is, let's say, for instance, aluminum, okay? This will be the last example that we go through before we get to your activity. Okay, any questions about what a group is and why that is so important? Because that column number will tell you how many valence electrons and why are these so important. In the outer energy level, what do they do? It's the reactivity. That's right. Does everyone have this content that wants it? Okay. So what we're going to do is we said aluminum, right? Okay. I don't think we can see that color. Okay. How do we identify aluminum besides this? What number? Okay. So that 13 in the middle, why is that important? Right. And if the atomic mass for aluminum is 27, what is that going to give you? Why is it 14? You subtract this number, the atomic number, or protons, from the atomic mass, which is protons and neutrons together, so that gives you 14 neutrons. Following our slide rule, okay? What are we going to put in that energy level? Okay? And we're not just making that up. How did you know that? Because it's 1s2. The slide rule tells you that. Okay? Then what? Add another energy level. Okay? And what two numbers do we put in this energy level? 2 and 6. Okay? Because these numbers on the outside have to coincide with this one on the inside. Because remember, protons have positive charges, what do electrons have for a charge? Negative charge. Okay? So then you can always check where you're at. What do we have on what number? 2 and 2 and 6 gives you 10. So simple math, we hope. 13 minus 10 must mean how many more do we need to do? 3 total. Okay? But we're not going to just write the number 3. You have to add another energy level. Okay? Okay? And then what? And if you want to put in a number 1 there, that's fine. Okay? Put a number 1. Whatever works best for you. But one of the things that I just like to do myself, the last electron or electrons that enter the orbital, I just like to put a box around there. Okay? So now, one of the things that we can tell, okay, remember, vertical columns, because you mentioned hydrogen and lithium have how many valence electrons? 1, because they're in the first column. Okay? Beryllium, magnesium, calcium, strontium, rubidium. No, not rubidium. Strontium and barium. They're in column 2. Why is that significant? It has 2 valence electrons. Okay? And we just wrote this down. What do we say you do with these middle block elements, the D block, our transition metals? We said skip over those. Okay? Because when we're talking about the number 8, it's these 2 plus these 6. So when we say column 1, column 2, column 3, 4, 5, 6, 7, and your noble gases here in column number 8. Okay? So, what column is aluminum in within this entire period? It's in column 3. Why is that number 3 so important? It has 3 what? There they are. 2 and 1, those are your valence electrons. So what does that aluminum want to do with those 3 valence electrons? What is it? Push them out. Get rid of them. Okay? So then, once that happens, okay, and this is why we say electrons determine its reactivity. I just said it. I bet it's under here. No? Did it get up and walk away? Purple. It's not. Okay. Well, this will work too. Okay. So then. Oh. Okay.
Same thing.
What happens to the best of us? Okay. So now, how many positive charges are in the center? How many negative charges are on the outside? How many are on the outside? 10. Okay? So now, once you look at aluminum's box, okay, what does it say in the upper right-hand corner? Plus 3. This is why it says plus 3. Because you've got 13 and we've got 10. You add them together, you get plus 3. That's why that has a number plus 3. Okay? We've now formed an ion. It's no longer neutral. It's got a positive charge. Okay? So, if these elements want to form, we'll just keep it simple, like fluorine, for instance. Okay? And we've done this multiple times. Okay? 1s2. Okay? Then what? 2s2. Now careful. In the P block only, what column is fluorine in? Okay. The reason that's important, okay, what column is fluorine in? In the entire period. It's in the 7th column. We know that because add these two together, that gives you the number 7. Okay. If it wants a valence, in other words, out here, if it wants 8 electrons out there, okay, how many more does it need to gain? So if we put another electron here, we've got 9 on the inside. Numbers and letters added together gives you what? Gives you 10. Oops, I put that on the wrong side. Okay. Then once you add these together, what do we get? What does it say in the upper right-hand corner of fluorine? -1. So keep in mind, metals, okay, column 1, 2, all of these here, but we're not going to do those yet as Bohr models until we get to these. Column 3, 4, 5, 6, 7, and 8. If it's in column 5 and over, it wants to gain electrons. If it's in column 4 or less, it probably wants to get rid of those electrons. It's all about trying to get an outer energy level of 8. You might say, well, this outer energy level doesn't have any. Well, that's true. But what does this outer energy level have? 8. So it is chemically stable now. Once you get to that number 8, that element is stable. Okay, middle. Okay, middle row or back row right corner. Back row left corner. Front row left corner. Okay, front row right corner. The rest of the front row. Then the rest of the back row. Okay. So we're going to start our activity now. So we will, as far as this is concerned, we'll stop here. Well, we can get these directions. And what we're going to have you do is Bohr models. You can write these out, but we have a special way to illustrate these electrons. So, does fluorine and iodine have anything in common? Element 9 and element 53. They're both in the 7th column, so they've got similar properties. We just illustrated with fluorine. How many more electrons does it want? Okay, so that's why you see these two numbers don't add up, because it's in the 7th column. So once this gets one more electron to make 54, iodine will have a charge of negative what? Negative 1. And we're going to have you illustrate that too. Okay, so with your lab partner that you have, Mr. Wagner, if you could hand out those salad boats or whatever you want to refer to them, and we'll start illustrating these Bohr models. A little bit of direction with your Skittles / electrons. Okay? I don't even know what colors these have. So the sour Skittles have what? Red, yellow, green, orange, and purple. Okay. S block electrons, how about we make purple? Okay? So purple is S. Okay? Then we've got green. Okay, let's go ahead and make those. Green is P block electrons. Then looks like we've got red. Okay? So red are D block electrons. Okay? And I think when we get all the way up to SM, which is samarium, okay, we need one more block, and that is what? F block. So we'll go ahead and make those orange. Okay, so please knock these out in this order. Do sulfur, vanadium, indolium, samarium, and then this is your last one. Okay, go ahead and start knocking them out. There's questions about what we do. Okay, these should be in energy levels like this, so your Skittles are like this, arranged like that, and then different colors. Okay? The input we asked for said we understand, so please knock these out, and we'll go forward from there.